Chapter 10, Rigid Body Dynamics, Part B, the Inertia Tensor. In the previous lecture, we saw that when two masses orbit around a common center of mass point, the angular momentum and the angular velocity were found to be parallel. So the angular momentum is a vector that points up perpendicular to the plane of motion, and so does the angular velocity. In this case, the angular momentum is parallel to the angular velocity vector, and the constant of proportionality is the rotational inertia. If the two masses are orbiting around not each other, but are displaced vertically, so the top mass orbits around above the xy plane and the lower one, say, orbits below the xy plane, we found that the angular momentum and the angular velocity vectors are not parallel. So in this lecture, what the goal of this lecture is to find a relationship between the angular momentum and the angular velocity that is general. What we're going to find is that instead of having a constant proportionality, we're going to find a quantity that is called a tensor that relates the two vectors. In this lecture, we'll look at solid body rotation. So imagine, say, if you have a satellite that's made of all these pieces, you've got solar panels and the main part of the satellite. We're picturing this thing rotating around as a solid object around a given axis. In this first approach, we're going to consider only rotation around the z-axis. So let's let this vertical yellow line indicate the z-axis that the satellite is spinning about. The total angular momentum of the satellite can be found by just summing up the angular momentum of all of its parts. And those angular momenta are the cross product of the position vector of the object with its momentum, or mass times velocity. So in this case, let's suppose that our origin is right here at the base of that red position arrow, that position vector. So if that's the origin, here's our position vector, and we take the cross product with, say, a particular object with the velocity to figure out the angular momentum. So since it's spinning around an axis, every piece of the satellite can be thought of as tracing out a circular path around that axis of rotation. So particles that are farther away from the axis will trace out a larger circle. Ones that are closer in will trace out a smaller circle. It turns out that the tangential velocity of a given part of the satellite is equal to the angular velocity cross the position vector of the object. So for example, again, if this is our position vector showing that part of the solar panel, if you take the angular velocity vector, which is pointing straight up, take the cross product of that with r, then you get the velocity vector like this, which is tangent to the circular path as it's going around. All right, so let's evaluate this tangential velocity given the fact that the angular velocity is directed in the z direction. So we'll just evaluate this cross product. So we write the determinant of ijk across the top. The first vector comes on the middle row, so it has 0 components in x and y, and a z component. And then we write x, y, and z components of the position vector. So when you evaluate the determinant, this is what you get. You get an x component and a y component, but no z component. So, which makes sense because our velocity vector, we know, should be parallel to the xy plane. So it should stay in this plane, so it makes sense that there isn't going to be a z component. We can now take this expression for our velocity and plug it in for the velocity and the angular momentum expression. So we'll evaluate a second cross product now. So we write the components of our position vector in the middle row, and then the velocity vector that we just calculated on the bottom row of the determinant. So when you evaluate this, this is what you get. You get x, y, and z components. Notice that the x and the y components look kind of similar. They're both negative terms proportional to either x or y times z. And then the last term is x squared plus y squared in the z direction. So this is an expression for what the angular momentum is. I should emphasize, notice that this is not necessarily parallel to the original angular velocity vector, right? The angular velocity vector was pointing in the z direction. This does have a z component, but it also has x and y components also. Okay, so let's look at this a little bit more. I'm just copying over. This is the expression from the last page. We can break this into components. So the x component I just wrote over here. That's the x component of the angular momentum. This middle one is the y component, and then that's the z component. Remember that the angular velocity has only a z component. Notice that each component of the angular momentum is proportional to the angular velocity. So there's an omega z term here, here, and here. This means that we can recover relationships that we're used to from physics 203. So we're used to writing angular momentum is the moment of inertia times the angular velocity. And so we have a term like this, but one way of interpreting this is that there are multiple moments of inertia for a given object. So the IZZ moment is just defined as all of the constants of proportionality between the z component of the angular frequency and the z component of the angular momentum. The IYZ moment is defined as the constants of proportionality between the y component of the angular momentum and the z component of the angular frequency, and the xz moment is the constant proportionality between Lx and omega z. So just by, you can just look at these expressions and just write down all the terms that are in front of the omega z, and here are expressions for IZZ, IYZ, and IXZ. So these are the results from the previous page. I've just kind of written them again. One thing to notice is that this term here, the IZZ term, depends on an x squared plus y squared, which is simply the square of the distance from the axis of rotation to the mass element. So, just using the Pythagorean theorem, x squared plus y squared is the hypotenuse squared, so that's just that distance. This should look familiar from, again, physics 203 when you wrote that the moment of inertia of a point mass is mr squared, where r is the distance from the axis out to the object. So again, r squared is just the same as its components, the sum of its components squared, x squared plus y squared. So this expression should look very familiar to you. So one question to ask is, when can we write down this expression that we're used to from physics 203, that the angular momentum is simply proportional to the angular velocity, with a constant being the rotational inertia? We want to keep this term, but we want both of these terms to go away in order for that expression to be true. So the question is, when do those terms go away? For what kinds of mass distributions do the I xz and the I yz terms vanish? So in other words, when is the angular momentum vector parallel to the angular velocity vector? So this happens in a number of situations. We're going to mention two of them right now. So one situation in which the I xz and the I yz terms vanish is for rotational symmetry. So if you have an object like, say, a top, and it's rotationally symmetric around the axis of rotation, then both of those terms will be zero. You can kind of see that here. So if I kind of look down on the top, here's X, here's Y, and you've got a rotationally symmetric object. If you've got a mass element here, and it's got, say an X component and a Y component like that, and that mass element has an equal mass element on the opposite side, so it has, say, the negative X and a negative Y value, then the contributions of these two mass elements will cancel out in each of those terms. So whenever you have rotational symmetry, you'll get pairs of mass elements that always cancel out. So that's one case. The second case is if you have symmetry through the xy plane. So for example, if we're saying that the z-axis is coming straight up, if you have a mass element that's above the xy plane with a positive z value and then one below the xy plane, so if for every mass element that's above the xy plane you have one below the xy plane, then the z components here will, there'll be pairs of z components, one positive and one negative, and those will also cancel out that summation. So in each of these cases, for these two kinds of symmetries, our standard result that the angular momentum is I times omega works. Let's look at one of the examples we saw a simulation of in the last lecture. So we have two masses. They're at a height z above the xy plane, and they're spinning around the z-axis. So if the coordinates of one of the masses is x naught, y naught, z naught, the coordinates of the other are negative x naught, negative y naught, and then z naught. So we want to find the angular momentum of this system. So we start with calculating the moments of inertia. So IZZ, IXZ, and IYZ, these are the expressions. So the summation is over our two masses. So for the first mass, it's m x naught squared plus y naught squared. Because these are squareds, the negative signs will just get squared, and and these will be the same. So the answer is just going to be 2m x naught squared plus y naught squared. For the IXZ term, we'll have, say, this mass will have a contribution of minus m x naught z naught. For this other one, we have a negative x naught component. So we have a negative x naught here. These two terms will cancel out to 0. Same thing happens with this term. We'll have a negative y term canceling these two out, so you get 0. So we see, as expected, that the Lx and the Ly angular momentum components are going to be 0, which means that our angular momentum vector is going to be parallel to omega. So it's going to be just pointing in the z direction. And this is its magnitude here. So in this case, this case is kind of a special case of one of the examples on the previous page. So if we take this one and you rotate it by 180 degrees, this one will map over to there, and so that's when you get these Lx and Ly terms going to 0. All right. So now we want to think about the general case. So we don't want to be restricted to just rotations around the z-axis. We want to have any axis be the rotation axis. So we can do it pretty straightforwardly by applying the previous method to the x and the y axes. So we write the angular momentum like this. We write the velocity vector like that, where now our velocity vector could either point in the x direction or in the y direction. And so when we do the calculation, we get 6 more equations. So these are the equations over here for rotation around the z-axis. These are the equations you get for rotation around the y-axis, and these are the equations you get for rotations around the x-axis. I've organized them in a special way. So remember that the second index is telling us about which component of the angular velocity this term corresponds to, and the first index corresponds to which term of the angular momentum this term corresponds to. So I've written it so that the rows correspond to having the same component of angular momentum. So there's an x in the first index for each one of these, and then y on the middle row, and then z in the last row. The columns are for the angular velocity components. So the first one is for rotations around the x, middle is rotations around the y-axis, and the final one is rotations around the z-axis. Because of the way that these are indexed and organized, we can actually write these equations more compactly as a matrix or as a tensor. So all I've done is just taken these equations and then just put brackets around them. Okay, and then called this quantity or this structure the inertia tensor. So we're making the moment of inertia now a bolded symbol. It's a tensor, and the tensor has 9 components. These are the values. They're just a shorthand way of writing the set of 9 equations. Okay, so let's just look at a few properties of the inertia tensor. So it turns out that the diagonal elements, the ixx, iyy, izz terms, all have a very similar form. They're all the sum of the squares of the 2 corresponding components. So, y squared plus z squared, or x squared plus z squared, or x squared plus y squared. The off-diagonal elements are symmetric, so the ixx term is equal to the iyx, ixz is equal to izx, and iyz is equal to izy. So what this means is that even though there are 9 elements of our inertia tensor, there are only 6 independent ones. So there's really only 6 calculations that you need to do to calculate all the elements, because these elements down here below the diagonal are just equal to the ones above the diagonal. So how do you use the inertia tensor? Well, so it turns out that this equation, L equals I omega, you can solve using matrices. So we have the inertia tensor here as a 3x3 matrix. We're going to write the angular velocity vector as a 3x1 matrix, and the angular momentum vector as another 3x1 matrix. So you remember how this works. Like, to evaluate this, you take the top row of the 3x3 matrix and multiply it element by element by this vector to get that top one. So like this. So Lx would be Ixx times omega x. So you take Ixx times omega x plus Ixy times omega y. So Ixy times omega y, and Ixz times omega z. Ixz times omega z. And similarly for the other rows. So the y component of the angular momentum is the middle row of the tensor times the angular velocity vector, and Lz is the bottom row times the angular velocity vector. Okay, so let's look at an example. Let's look at the case of a point mass in the xy plane. It's going to have an x component A, a y component B, and a z component 0. Okay, so I'm going to try to organize this information in a little table up here that we can refer to. So the x component is A, y, B, z is 0. X times y is just going to be a times b, and x squared plus y squared is going to be a squared plus b squared. Okay, so we're going to use this to evaluate the inertia tensor. So let's look at this. The first term, the ixx term, is y squared plus z squared. So z is 0. So this is just going to be mb squared. So we write, we're going to factor out an m out in front because that's going to be present in every term. And so we'll just write the other part in our matrix. So that top left element of our tensor, of our matrix, is just b squared. Iyy is x squared plus z squared. Again, z squared is 0. X squared is just going to be a squared, so you get an a squared in that second diagonal term, the iyy term, and izz is a squared plus b squared. So you get a squared plus b squared in the lower left element of our matrix. All right, let's look at the off-diagonal terms. Ixy. Okay, so let's look at the off-diagonal terms. So Ixy, which is Iyx, is negative m x times y, so minus mab, so you just get a minus ab in these two off-diagonal terms. The yz and zy components are 0 because you're multiplying this term by a z, and z is 0, so this term and this term are 0. Similarly, for the xz and zx terms, those are also 0 because you've got a z in there, which is 0. So these terms here and here are both 0. So that's it. So it wasn't too painful to calculate the tensor. So we see that there's some 0 terms in there. Yep. And now we can see how to apply it. So let's take our tensor and apply it to a rotation around the z-axis. So we want to spin around the z-axis. So we're going to apply the tensor that we just got and apply it to a vector angular velocity where you only have a non-zero term in the z direction. So omega x and omega y are both 0, omega z is non-zero. So we're going to multiply our 3x3 matrix by our 3x1 matrix to get this. So in the first one, b squared times 0, negative ab times 0, those don't contribute anything. And then now this one has a 0 times omega z. So this first result is just all 0. The second row, similarly, it's got a similar structure. So again, you get 0. The last row, however, you get 0 times 0 plus 0 times 0, but then you get omega z times a squared plus b squared. So the result is that the angular momentum vector is m times a squared plus b squared times this vector, but it's only got an omega z component. So what that means is that the angular momentum vector points in the z direction because the other components of it are 0. So in this case, we find that the angular momentum vector points in the same direction as the angular velocity vector. So you could just write L equals I omega, where I is just a regular scalar for this case. So L is proportional to omega. And you can just write that, yeah, L is this constant proportionality, angular, the rotational inertia times omega. Again, because L is pointing in the same direction of z, it's going to be constant in time, and since it's not changing, then the net torque is going to be 0. So no torque is needed to keep this mass orbiting around. Now you do need a force, right? So in order to swing this mass around the origin, you need to pull, maybe this mass is attached by a string to the origin. So to keep it moving in a circle, you're going to keep pulling or exerting a force on the mass, but not a torque. mean, it should be easy to see why the torque is 0, right? Because the force needed to pull this mass inward to the center, well, that force goes right through our origin. So whenever the force goes through the origin, the torque is 0. Okay, let's spin the system around a different axis. So let's pick the x-axis now. So now we're going to spin it this way instead of this way. So we have an omega x here in the angular velocity vector. So when we do the matrix multiplication, so now you get a term showing up from the top row. You get a b squared times omega x, so you just get m omega x b squared. But then the second row also gives a contribution, negative ab omega x. You get a negative ab there. So what this means is that the angular momentum vector has both an x and a y component. So it's in the positive x direction, so this way, and a negative y component, so a negative y this way. So it's like coming out this way in the xy plane. So L and omega are not parallel. What that means is that the angular momentum vector is going to precess or to rotate around the angular velocity vector. So the angular momentum vector will trace out this cone that's kind of pointing out along the x-axis. In order to maintain this changing angular momentum, you need an applied torque. Okay, so those were a couple of simple examples. Just in passing, we're not going to spend a whole lot of time doing this. You might do this in a calculus class. But if you want to calculate the rotational inertia of a solid object instead of just point masses, you simply replace the summations with volume integrals. So all of those quantities that we had before are replaced with integrals. We mentioned this before, that when you have a solid object that is rotationally symmetric through the xy plane, then the off-diagonal terms containing the symmetry variable vanish. So let me say that again. So look at the structure. Look at the structure of the non-zero entries in the inertia tensor. If it is symmetric through a transformation where you switch z with negative z, then the off-diagonal terms that include a z go to 0. So if you had a symmetry plane through the x-axis, then it's the off-diagonal elements that include an x. Those would be the terms that go to 0. And it turns out that if you have an object that has has symmetries along 2 or more perpendicular axes, so that if you replace x with negative x, or y with negative y, or z with negative z, if you have 2 axes where that is true, then all of the off-diagonal elements go to 0, right? And so you would have your rotational inertia tensor would be purely diagonal. And this is like a special case. We're going to come back to examples like this in the next lecture. Okay, so in summary, what we've seen is that if the angular momentum and the angular velocity vectors are parallel, you can use the simple relationship from Physics 203 that the angular momentum is proportional to the angular velocity, where the constant of proportionality is the moment of inertia, which is a scalar. If L and omega are not parallel, you've got to replace that angular, you've got to replace that rotational inertia scalar with the inertia tensor that we've been talking about in this lecture. Okay, so in the next lecture, we'll talk about principal axes, which are special coordinate systems that diagonalize the inertia tensor. And those have special properties when you actually have something that's actually rotating in space.